today. So here I call it self-cleaning floc filter settler. But whatever that floc filter settler is, think of that as temporary words, and maybe you will help me figure out what we should actually call this. So I want to put this in context. Where does this fit? And so we'll begin with a discussion of where sedimentation fits in a traditional conventional water treatment plant design, and then what it looks like in an AguaClara design. And then we're going to talk about various pieces. We'll talk about the whole unit as one, the floc filter sed, and we'll look at some pictures of plants, both schematics and also plants under construction. Then we'll delve into the floc filter. We'll talk about how the flocs are resuspended. We'll talk about floc hoppers, and then we'll talk about what's happening at the top of the sedimentation tank, which is actually where sedimentation is happening. So we'll talk about capture velocity and in the context of plate settlers, and we'll talk about a crazy phenomena called floc roll-up. So that's what's coming over the next 2 weeks, 4 lectures. So here's a conventional water treatment plant. You take a raw water, a surface water, a creek, a stream, a river, a lake, and you run it through an entrance tank where you screen it, remove grit, and you measure the flow, get rid of any sludge that comes out of that, any grit. You add a coagulant in a mechanical rapid mix. Then you go to a mechanical flocculator. Then you go to a sedimentation tank where sludge is removed, and often there's a mechanical system for scraping the sludge out of the bottom of the sedimentation tank. And you go to a rapid sand filter, usually a dual media filter where there's anthracite and sand. And then there's backwash water that comes out of that. And you go on to disinfection and to storage and to distribution. Okay, so that's the whole picture again, to remind you where we're at in this story. And the piece that we're focusing on is sedimentation. However, in an AguaClara plant, it looks a little bit different. So here's an AguaClara plant. We bring raw water in, we do the same things in the entrance tank. And then we currently don't think that rapid mix has any significant role, and so we're not including it in our design, and we're going straight to hydraulic flocculation instead of mechanical flocculation. And you are now becoming experts on hydraulic flocculation. And then there's a new process, which we're calling a floc filter. It's in the literature, it would be referred to as a floc blanket. And I have rebelled against that term ever since I first heard it, because it is not cozy. You cannot use it to wrap yourself up and keep warm. And it doesn't look like a blanket. And so it's not clear why the term blanket was added to that. And so now that we, as of about a year ago, have a much better idea of what the physics is, of what's going on inside that system, we're going to call it a floc filter. That's in the bottom of this sedimentation tank that we're going to be studying. Then there's 2 places where the water goes from that floc filter. It either goes to a floc hopper where the sludge is discharged from, or it goes up to the plate settlers, and out of the top of the plate settlers is where the clean water goes. That goes on to a stacked rapid sand filter that has backwash water as well, just like a conventional filter, and then storage and distribution. So the very end of the system looks identical again. So we're in this middle part now where instead of just a sedimentation tank, there's a floc filter, there's a floc hopper, and there's plate settlers. And we're going to figure out how those things work. So this is a side view of this system. And I want you to slowly begin to learn how water flows through this system, because you have to understand how water flows through the system and how particles flow through the system so that you can begin to understand how all these pieces fit together. So the blue dots are my pretend water molecules. They're humongous water molecules that are in the inlet channel. That inlet channel has flocculated water that just came out of the flocculator, okay? And that inlet channel flows across these pipes, and so the water can enter those pipes and go down into the inlet manifold, which is in the bottom of the sedimentation tank, go through some diffusers, up through the floc filter, up through the plate settlers, and out the outlet manifold and over to the filters. Okay? Any questions about the path of water through this unit, this floc filter sed? I am keenly aware that some of this is confusing, like trying to imagine what actually is happening. So you should not be surprised if you're confused. And I have a hard time anticipating how to answer your unspoken question. So if you have a question, don't hesitate. Like maybe you're wondering, why does the water go down at the bottom of the sedimentation tank and then back up? I will show you another view of that. The water is forced down because there are little pipes that it is forced to go in that take it to the very bottom of the sedimentation tank. And then there's a little, what we call a jet reverser, that turns it around and sends it back up. So I'll show you another view of that. The inlet manifold and the outlet manifolds are literally just pipes that have either diffusers connected to them, which are little like 1-inch diameter PVC pipes, or little holes drilled in them, orifices where the water enters in the case of the outlet manifold. Another key thing to see in this drawing is there is this exit weir that's right before the outlet channel. And that exit weir is what controls the water level in this tank. And actually, that exit weir is the first place where the water does a free fall since the LFOM. So in the linear flow orifice meter, water does a free fall and basically drops into the upstream end of the flocculator. And then there's head loss as it goes down through the flocculator. It enters this inlet channel. It goes through the sedimentation tank or floc filter sed, and then it exits and goes over another weir where there's free fall. And that means that this weir where there's free fall controls the water level all the way back up to the LFOM, to the outlet of the LFOM, or to the very beginning of the flocculator. It means that if you turn the water off, think about this for a second. If I turn the water off to the plant, what determines the level of water in the flocculator? There's no longer any flow. And granted, you have to give it a few minutes for everything to like calm down. And once all the water stops flowing, what level will the water be at in the flocculator? Who wants to be brave?
Is it the height of the water in the entrance tank?
Dan, I'm going to be hard on you. It's not. I'm sorry, it's not. But somebody else want to try? Because getting this insight is key. It turns out the entrance tank has no influence on this. Go ahead, I can't hear you anyway. You're not muted, but I can't hear you. Try again, Dan. Somebody else want to jump in? So I didn't mean to humiliate Dan. I hope I didn't humiliate Dan. Dan, you're fine, right? Good. So it's not the entrance tank. It's not the LFOM. What is the idea here? This is like a very slow moving stream, and there is a dam at the end of on the stream. The water level upstream from the dam is controlled by the dam. And if the water flow rate were to completely stop, it would be that dam that would set the water level upstream.
Can you hear me now?
Yes.
Did I fix it? Okay, cool. No, I said the height of the water in the sedimentation tank, like where the water's leaving into the outlet channel.
Perfect. Did I
Sorry, I
completely
said that like
misunderstand?
forever ago, but I guess I was muted somehow.
Perfect. Yeah, that's exactly right. So it's this weir, which is right here under my cursor. That weir is what sets the water level in the sedimentation tank. That will become the water level in this inlet channel, which is the same as the water level exiting the flocculator. And because there's no flow in the flocculator, that will end up being the water level the whole way back up to where the LFOM dumps water into the flocculator, or the very, very beginning of the flocculator. Okay, that was great. So that's this tank and how water flows through it. Here's another view of it, showing what the diffusers, more about what the diffusers look like in the bottom of the sedimentation tank, and showing this idea of a jet reverser where there's a PVC pipe 3 inches in diameter that's cut in half, and that's embedded in the concrete in the bottom of the tank. And the diffusers are literally blowing water into one side of that half pipe, and then the water is going around in a circle and coming out the other side. And the plate settlers in the effluent manifold. So that's another view. Here's yet another view of this same system, showing an end view, an isometric kind of angled view, and a top view. And I want to just give a chance for you to look at this for a couple minutes and see what questions you have. So you can chat questions or however, and what questions you have about how this all fits together.
What are those tiny white pipes at the bottom near the end, closest to us?
This one? Or
yeah, in either view.
okay.
It's the right place though.
This one is a tiny little 1-inch diameter diffuser. It takes the water from the inlet manifold and forces it to go straight down into, there's a little jet reverser right here. And so the water goes straight down, it exits right here, and then turns around and goes up. And we'll talk more about why that happens. It ends up being a key part of our design. You might also wonder, like, what are these small valves draining? Those are draining the sludge out of the floc hopper. Anyone else have another question about this? Okay, we're going to keep on going, and there'll be like, we'll be going over the pieces of this more and more, and so this will become clearer if there are questions. That weir that I'm pointing to is how flocs get from the main part of the floc filter sed system into the floc hopper. They flow across that floc hopper, and I'll show a movie of that. And that's what controls the water level of the sed tank. That's that weir that I talked about earlier. And there's a pipe that an operator could potentially drop a light on a string, a submersible light, a flashlight that's submersible, down into the floc hopper and be able to see when the light goes dim as a way to see how deep the sludge is in the floc hopper. So those ports are right here and here, and they line up with the very center or the very lowest part of the floc hopper. Here's some views of workers fabricating these systems, building these systems in Honduras. So they're making the sloped sides bottom of the sediment, excuse me, of the sedimentation tank. Wait, yeah, so I'm asking for your help. We'd like a name for what this system is. It's a self-cleaning with floc filter and plate settlers. It's a whole lot more than just a conventional sedimentation tank. And I'm calling it a floc filter sed in these notes, but we're looking for a better name for this. So here's another view of this floc filter sed. The ledge that you see along the side here is a ledge that will eventually be used to help support the plate settlers. So the plate settlers will be sitting on that on their edges, on the sides. This platform here is where there will eventually be our system of 4 channels that control the inflow and outflow into this system. And of course, these are the dividing walls between the different units. And you can see the construction here. For those of you who are interested in the structural engineering side, they use a very different way of laying bricks. If you think about bricks, you always want to lay them so that they're overlapped with each other, but you notice here they're not. And the reason is that these are load-bearing walls that have to be waterproof and have to resist significant hydrostatic pressure, because you have to be able to drain one tank while the others are still online. And that means there's the full water pressure pushing on these walls in either direction, depending on which side you drain. And so to accommodate that, there's rebar. And you can see the rebars here. There's rebar that goes right down through between the bricks. So in the mortar, in both directions, both horizontally and vertically, there are rebars embedded, and that's what makes this be a reinforced masonry wall. There also are beams. Sorry, I should know my structures better than that. There are columns, and you can see columns here. These are poured concrete columns in the middle of the wall. I would hesitate to make a case for why that is essential, but that rebar, of course, goes down into the slab below, and that's part of the structural design for making sure these walls are strong enough. And in case it wasn't clear, these in the back are going to be windows eventually in this building. Oh, and you notice brick walls in here, no overlap between bricks. Brick walls out here looks conventional. The bricks are like this. Do you see that difference? Walls that have to hold back water, the bricks are on top of each other so they can run rebar in them. Walls that are just building walls have bricks overlapping and they're not reinforced. See, if I wouldn't have pointed that out, you might not have even noticed that those bricks were different, right? Here they're getting ready to pour the concrete for the slab that will be the bottom of the 4-channel system that controls the inlet and outlet. These are the couplings, the pipe couplings that will be embedded in the concrete that are the inlet manifold. So they're connected to the inlet manifold. And you can see here I have a second view of this. This is an inlet manifold identical to the ones that you see over here, where there's a line of 6 of them. So here's one of those, and that pipe goes down and then comes out at us in the very V at the bottom of the tank. And that pipe will eventually have those diffusers in the bottom of it, pointing the water to the very bottom of the said tank or said floc filter. Okay, they've poured the concrete, so you can see this thing coming together. And you might wonder, like, what are these pipes for? Those pipes are going to eventually carry the settled water, the clarified water, to the filters. And Oh, I'm looking, look, there's this guy with the blue hat here. And he's got like a garden hose or some sort of a small water hose. And I'm curious, has anybody seen construction in other parts of the world where you don't actually use a theodolite to do leveling, but instead you use a hose, a water hose? So it turns out this is a pretty accurate way of doing it. That water hose is transparent, so you can see the water inside the hose, and you set the hose up so that there's a little bit of air at the end of each end of the hose, and you can use the water level in that hose. And that water level, of course, is the exact same level on both ends of the U of the hose, no matter where you drag it on your construction site. And so you can use that to mark a level over a relatively long distance. Wow, if that didn't make any sense, I'm sure if you look up water level on YouTube, there'll be somebody that will show you a nice image of that. This is the fabricated inlet manifold upside down with the diffusers pointed up. Those are the diffusers that will be pointed down and will be delivering water into the very bottom, flocculated water into the bottom of the sedimentation tank. And those diffusers are made in a very cool process. And I forget if I have any images of that, but they're made by heating up the PVC in hot vegetable oil on a little stove. And it just needs to go to a temperature a little bit above boiling, just a little bit above 100 C, and then that's enough to soften the PVC so you can mold it. Here they're making the plate settlers. The plate settlers are made with polycarbonate sheets that are normally used as a transparent roofing material. The sheets are about 1 millimeter in thickness, and then they're spaced apart using a system of pipes. So there's a 1/2 inch PVC pipe that goes the whole way through a bunch of sheets. And then there's a set of 3/4 inch PVC spacers that fit over the 1/2 inch pipe and that create the space between the plates. And there's a view of the finished sedimentation tanks. This is in a single sedimentation tank in a very small plant that doesn't, because it's so small, it doesn't actually have the inlet and outlet channels. It just has a pipe, pipes that send the water into the tank and out again. Okay, so that was an introduction to get you thinking about what this system actually looks like. I want to also remind you of, like, how did we get here? We just finished flocculation, and if you think about Swot, which is strengths, weaknesses, opportunities, and threats for flocculation, and think about what we're trying to do with Swot, safe water on tap. Here's what was great about flocculation. It rapidly reduces the number of primary particles, the raw particles that were present in the surface water. It reduces the concentration of them by converting them into flocs, okay? So it produces flocs that can be captured by either sedimentation or filtration further downstream. The weakness of flocculation is that it always leaves a significant number of those primary particles that haven't flocculated. And getting the last ones out is a real problem, because remember the issue? Those small particles can only collide with other small particles, and there aren't many small particles left. And so it takes a long time to get a collision between those remaining small particles. And so it takes a really long time to significantly reduce their concentration. Their concentration, if you start out with 1,000 NTU water, really, really turbid chocolate milk, the concentration of unflocculated particles reduces super fast initially, but then it slowly goes to a crawl as the concentration keeps on dropping. So that's the weakness of flocculation, and hence we're going to try to solve that in the next step. And this was a reminder of why. So the small particles can't collide with the big flocks because there's this boundary layer around them that's spinning with the floc. And so the small particles just breeze right by and never come into contact with the floc. So that's our problem. And now for something completely different. This is what I did on Sunday. I created a new animation where I attempt to describe almost everything, not everything, but almost everything that's happening inside this floc sed system. And in order to do that, I had to simplify it a little bit. But this is just, it's a simplification that just helps us think about what's going on. And so there are 4 categories of flocs that I want to introduce you to. So the blue one is a new floc that is brand new, and it is just joining the floc filter. And I'll explain where it comes from in a little bit. The blue and red dot floc is a floc that's in the floc filter that has become full of clay particles or other small particles. So it's taken on additional particles inside of itself and become full. The red particles are the primary particles. These are the bad guys, the clay, and for that matter, the cryptosporidium that we really do not want to drink. Or it also represents flocs that are too small to be captured by the plate settlers. So remember, each of these particles is really a type of particle, and there's a range of sizes in each one. And then the green one represents the flocs that settle fast enough to be captured by the plate settlers, but not fast enough to stay in the bottom of the sedimentation tank, in the bottom of the floc filter sed in the floc filter. So now let's go to the animation. So first of all, here are those 4 classes of particles again. And let's talk a little bit more about them. The smallest ones have a terminal velocity, their sedimentation velocity is less than the capture velocity of the plate settlers. And we'll talk more about what that means, like exactly how that works, but it means that they don't settle fast enough to be actually captured in the plate settlers. Wow, the next one gets more complicated. The green ones have a terminal velocity that is less than the upflow velocity in the sedimentation tank. So the water's going up in the sedimentation tank. These particles are trying to settle down, but they're settling down at a slower rate than the water's going up, so they're going up. But their terminal velocity is greater than the capture velocity required by the plate settlers, and so they are able to be captured in the plate settlers. So those are 2 of the small particle classes. The 3rd and 4th particles both have terminal velocities where they're settling so fast that they can stay in the bottom of this floc filter sed unit. So they're going to end up hanging out in the bottom. So here we go. Here's the inlet. This is coming from, it's bringing water from the flocculator into the very bottom of the sedimentation tank, or this floc filter sed. There's plate settlers near the top, and there's an effluent manifold. It's got orifices in the top, and that's taking water and any particles that don't get removed out the top. So what's coming in? In the pipe from the flocculator, there are a whole bunch of green guys. Green guys are the beautiful flocs that the flocculator made, okay? So that's great. They're coming out, but they can't settle very fast. And they can't settle fast enough to stay in the bottom of this floc filter sed. And so what happens is, well, we'll get to there in a second. I forgot the order of my animation. Okay, in the bottom of the floc filter sed are a bunch of these blue and blue with polka dot guys. And you're wondering how they got there. I'll show that kind of as we go through this. So for now, take my word for it. They're sitting there, they're kind of hanging out, they're settling fast. The water is moving up through them. And so it's called a fluidized bed. And I'm realizing that in our normal everyday life, we don't really encounter many examples of fluidized beds of anything. I'm curious, did any of you ever see a rapid sand filter being backwashed? Anyone? A rapid sand filter being backwashed? Looks like Ravi is the only one. So Ravi, you got to see a fluidized bed. The water is going up through the sand so fast that the sand ends up being fluidized, it moves around. And if you were to jump into that sand filter, please don't, you would sink right into that fluidized bed because it's no longer settled, there's no structure there, it's all a fluid, even though there's sand, which is not a fluid, but it acts like a fluid. This is a fluidized bed of flocks in the bottom of the sedimentation tank. And if you poked your fingers into it, you would just experience it as being water with lots of flocks in it. Okay, so now we're going to look at what happens to these green guys. Those green guys go right up through the floc filter because they don't settle fast enough. And then, oh, what's happening now? There was an avalanche on the plate settlers and they converted. Did you see that? This is one of the key conversions that happens inside the system. So let's do that again. So flocks from the flocculator go up onto the plate settlers, are captured on the plate settlers. They form an avalanche and they roll together and they form one of these brand new flocks that's going to now have a high enough terminal velocity that it can hang out in the floc filter. Pretty exciting. We just added a floc to the floc filter. Okay, what else is coming from the flocculator? Well, I just complained about the fact that in the flocculator, we fail at converting all of the red guys to green guys. So let's look at what the red guys do. So first of all, there's green guys everywhere in this system. So they're flowing. Matter of fact, their concentration is the same as in this system is the same as their concentration in the flocculator. So whatever's coming out of the flocculator is everywhere in the floc blanket as well, as an additional concentration of green guys. Now let's bring the red guys in. So the red guys also go up through. Oh, but it's so sad. Did you see what just happened? This was like what makes us cry. Okay, let's experience this again. Feel the pain. This red guy is going to pop in and it goes up through the plate settlers and it leaves in the effluent launder. And so what's our only hope for catching this guy? We've got a filter coming up and we're hoping that the filter will catch it. And then there's one more thing we can do. If it is a pathogen, we can nail it with chlorine at the end. But we're kind of bummed because we were hoping to remove that guy in this floc filter set, but we lost it. But there was two red guys that came in. So let's watch this again and now pay attention to the next one. So there was failure. Now another one comes in. And this one, whoa, did you see what happened to that? Did you see it? It landed right in the middle of a blue guy. Here we go again. First time failure. Second time, it came up and it went right into the middle of a blue guy. It went inside the floc and was caught there. So and I'll show more detail on what's going on with that. So we just converted a blue floc that was all blue, and we gathered its first red dot, and it's on its way to having lots of red dots. There's a problem with what I've drawn so far, and that is that I've got lots of particles coming into the system, and so far the only particles that have left was that one red particle that snuck out the top. And you all know that mass conservation is actually a thing. So there must be some other place where particles are leaving. And that's going to be, what did I forget? It's going to be a floc hopper that I'm showing here on the side of this floc sed filter. And every once in a while, a floc will pop across that weir. Well, every once in a while, a floc will pop across that weir and end up in the floc hopper. Oh, and did something just happen that makes you sad? Look at who went into the floc hopper. See, I'm beginning to like cast this story in terms of good guys and bad guys. Like green guys are good guys, blue guys are good guys, red guys, we don't really like them because when we drink them, we feel really bad. And blue guys that are full of red guys, this is kind of sad, they're useless. They get full and they're useless. So what's sad is that the floc that ended up in the floc hopper was one of the good blue ones. And it would have been so much better if it had been one of the blue ones with red dots that had already done all it could for contributing to society and had taken all the red guys that it could along with it. Wow, who wants to ask a question about that? Because, by the way, you are the first people that are ever learning about this system, because we didn't know about how much of this worked until the last year. I shared this with Kevin Sarmiento, who did the research that uncovered like a bunch of these secrets. I shared that with him on Monday. So he saw this and reviewed it and made sure that I was telling the story as best we understand it now. I'll give you a little bit of a story about how we learn these things, because I don't have like the optical tools to be able to actually watch much of this happening. And so we have to deduce it based on other things that we observe. So any questions about this story that I've told you?
I have a question.
Yeah.
Is there any specific methods that exist for getting the full flocks? Because the objective is to get the full flocks with all the red in the flock hopper, correct?
Right.
So can you institute like because I imagine the full flocks, those have either like they're a larger diameter because it has more things attached to it, wouldn't it?
Well, we think that these red things are actually inside the flock. So it probably doesn't have a larger diameter, but it probably does have a higher density and a lower porosity and a higher fractal dimension. And you're asking this question because, what are you thinking?
I'm just thinking of ways to ensure that the flock hopper only takes in full flocks instead of empty ones.
Yeah, this is like the edge of knowledge right here. Like we're trying to figure this out too. And we actually played with one idea, which was trying to change how the flock hopper works and try to collect particles from the bottom, the very, very bottom of the flock filter rather than off the top. And there's at least some evidence that that helps, but it didn't completely solve this problem. But there's hope for getting better than what we are now.
Would you try to get it from the bottom to would be using that that different different densities, is that why you would
Yeah.
do that?
Yes.
Okay.
Other questions? Could you tell the story of the red, green, and blue flocks? How things come from the flocculator, end up in this floc filter sed system? And I want to share this other crazy insight. You know, I've known about plate settlers for a very long time, and I don't think I've ever asked the question of how do flocks or particles that were caught in a plate settler, how do they get out the bottom of the plate settler and end up in the bottom of a sedimentation tank? So in a conventional system, there's not a floc filter. So there's not this concentration of blue and blue-red flocks in the bottom of a sed tank. The blue and blue-red flocks that I have here are because of our design that keeps them in suspension. But in a conventional sedimentation tank, those don't exist. They're all just in the sludge in the bottom of the sedimentation tank. So the question then is, how do the green guys that land on the plate settlers, how do they get to the bottom? And before creating this animation, I didn't realize how big of a question that was, and how the only way that they can get to the bottom is if they change their sedimentation velocity. Because the reason they got to the plate settlers initially in the first place is because they weren't settling fast enough to stay in the bottom of the tank. And so they went up to the plate settlers and were caught there. Now, the only way they can get back down to the bottom of the tank is if they increase their sedimentation velocity. And so that's what happens in plate settlers. It's a cool insight. Plate settlers act like little avalanche generators. And as the flocks are rolling down the plate settlers, they grow larger. And then they have a terminal velocity that's big enough that they can actually get to the bottom of the sed tank. That cool? Some cool, cool physics. Sedimentation just got more interesting, right? Okay, so now let's talk a little bit about what's going on in the floc filter. So the floc filter is a high concentration, it's a fluidized bed of flocks that is in a uniform upward flow. So the water is coming up, that's keeping all these flocks in suspension. In floc filters, small particles flow through the large flocks. So there's a large floc and small particles actually flow right through it. And as they're flowing through, there's a chance that they will collide and attach inside the floc. So that's this idea that flocks are filters. So when I call this a floc filter, it's in the same way that you could talk about a membrane filter. In a membrane filter, the membrane catches particles. In a floc filter, the flocks catch particles inside the floc. Okay, so now a more detailed animation of what's going on inside a floc. So this big floc that I have on the right is like a big blue floc that I showed previously. Just now I'm showing the detail and showing you actually it's extremely porous. It's this fluffy like snowflake, and it's hanging out in the floc filter, and water is flowing around it, and water is also flowing right through it. So those are streamlines, and some of those streamlines go right through the floc. Not many of them, but a few of them. And so the dark blue in the middle here represents the flow that actually ends up going through the floc. And the the donut between the dark blue and the outer blue ring represents kind of the projected area of the floc where that water goes around the floc. So the point is that most of the water still goes around the floc, but a small amount of it goes through, and that small amount ends up probably pretty efficiently being filtered by all of the particles that are inside the floc. So that ratio of the dark blue to the white is a function of the floc porosity or the fractal dimension, but think about it as floc porosity. If the floc is really porous, then lots of water can flow through it. If it's not at all porous, then the dark blue dot goes to nothing, right? If this were a non-porous sphere, then no water would be flowing through it. And that ratio that I've shown here would be 0. And it wouldn't work anymore. So let's animate this and show what's going to happen. So let's get rid of these streamlines, and let's bring a floc that came from the flocculator, and it's going to come up from the bottom of the screen, and it's going to either go around this floc, or maybe if we're lucky, it will go right through it. So let's see. Up, I lost that one. It just went around. Let's try another one. This one was closer to the center, and it actually went into the floc and got caught. Here's another one into the center of the floc and got caught. Another one got caught. And now the floc is apparently has some human characteristics, and it's feeling full. So the floc is like, oh man, I've just eaten a lot of clay. I'm feeling full. Another clay particle comes in, and it manages to, it goes into the floc and gets caught. Another one goes in and gets caught. And the floc is saying, oh my goodness, I'm stuffed. And now the floc's porosity has been reduced. So there's very little water that's actually flowing through the floc anymore. The water is instead flowing around the floc. And so now when we send another particle up through in that same spot, it just goes around the side. So this floc is now one of those blue flocs with lots of red dots in it, and it's full, and it no longer is capable of catching any more red dots. Anybody want to ask a question about that?
I have a question.
Yeah.
So is the floc no longer spinning like it was in the flocculator?
Great question. What do you think, guys? What made this floc spin in the flocculator? Anyone can answer. What made the floc spin in the flocculator?
Was it the deformations or like the velocity gradient caused by the deformations or something like that?
Yeah, you're exactly right. Look, the velocity gradient is what's causing the fluid to deform. They're like the one and the same thing. The fluid is deforming, and the velocity gradient describes how fast it's deforming. And it's that velocity gradient that's causing anything that's in that velocity gradient to actually spin. So here we have uniform flow up through, and although there is some shear associated with the fact that it's flowing around flocs, there's no big fluid deformation happening. So I'm not going to say that these flocs don't rotate at all, but there's nothing spinning them like there was before. Isn't that a great insight? So before we said this couldn't happen in the flocculator, but here the fluid dynamics are completely different. And so these flocs are not spinning wildly, they're just hanging out. And now this effect that water can actually flow through the floc because it's no longer dragging all this boundary layer around with it. And we have this new mechanism for capturing little particles. Anybody else want to ask a question? Okay. I want to end with this slide because this slide gives you a little bit of an insight into how we go about trying to figure out what's happening inside a process where you can't actually see it. So this is data, and I should have put a citation here. It's from Kevin Sarmiento's thesis that he just completed for his master's. And he was using particle counters that can count and size particles that were leaving a floc filter. And he's tracking, okay, on the y-axis, it's delta PC star. That means that from at time 0, when his system just began working, he called that 0. And this is, and so what he's tracking is additional improvements in performance since that time 0. So a delta PC star of 1 means that he's removing an additional 90% of the particles. And a delta PC star of 2 would mean he's removing an additional 99% of the particles. So here we're seeing time 0, he's basically set it to 0. And then we're looking at the improvement in performance. And over the next few hours, up to about maybe 7 hours, the floc filter is slowly. So I have a confession to make. I'm in the process of changing language about how we talk about this stuff. And I have just concluded that we should talk about these as floc filters rather than floc blankets. And I'm chuckling inside because one of the floc blankets leaked through onto this slide. So I didn't get rid of all the floc filters. So anyway, the floc filter is growing, and eventually it starts dumping into the floc hopper. And the moment where it starts dumping into the floc hopper is at like around hour 7. And you see that there's this very interesting trend. Okay, and there's all these different particle sizes ranging from 2 to 3 micrometers up to 33 to 65 micrometers. And then there's also just the turbidity meter that measures all the particles that are in there. And you see that there's little differences in the trends, but let's focus on the group of particles like between 2 to 3 and all the way up to 5 to 9 micrometers. These are mostly the clay particles that were introduced into the system, because there's a range of sizes within clay. And what we see is that they all got better as the floc filter was growing in depth. And then when the floc filter started dumping excess to the floc hopper, performance actually got worse. And this was a complete surprise to us. We didn't know this was happening. We had made a mistake, and we had done a lot of research where we built different floc blankets and we measured their performance as we were building them. And we hadn't done an extended experiment where we looked at how did that floc filter continue to work after it was running for days, because this is just a little over a full day that this experiment was running. And here we see that it gets worse and worse over time. And this made us think a lot about what could possibly be happening that makes it that when a floc filter reaches the floc hopper and starts dumping flocs, that it gets worse. And I showed you the hint of what it is. And it's that at that point, some of those beautiful blue flocs, before they've ever had any chance to capture any of the red particles that we're trying to remove, get wasted and dumped. Before that time, none of them get wasted because we're not wasting any flocs. So it's once the floc blanket floc filter gets to the floc hopper and starts dumping, we start losing some of those floc filters that we were counting on, the blue guys. And this graph is really like the origin of the animation that I showed about what must be happening with the fact that we have finite capacity in a floc. And once it is full, it's no longer useful. And we would like those to be the ones that leave, but unfortunately our system for getting rid of flocs is also getting rid of flocs that would have been useful. With that, I need to stop and let you go to your breakout rooms. So Patrick is going to send you to breakout rooms. You should have all received an email from me with the questions. And I want this to be like completely open. You reflect with the others in your room about how you've been experiencing assignments and learning and the challenges of learning and the fact that some of this is pretty hard stuff to learn. So I want you to talk about that. And I'm doing this because one of my insights has been that when something is hard, if you can identify what's hard and talk clearly about what's hard, then often you can figure out what steps might be reasonable to take to make it easier. Because if something is too hard, you have to do something. So I want to know what's hard and what your ideas are to make it better. So with that,
Monroe,
I'll
do
say
you want
goodbye.
them in their project teams or random rooms?